Fluorescent lights contain spectral lines from the light emission of mercury atoms. Special coatings on the inner surface of the light bulb help to attenuate visible frequencies, which can be seen through the diffraction grating reflection of a compact disc. Cut a narrow slit through some thick paper or cardboard and place it over a bright fluorescent bulb. View the slit at an oblique angle against a CD and look for spectral lines. And then the next one we'll do is an incandescent light bulb, and this says that it will be smooth, continuous spectrum with no lines because the incandescent filament glows at all visible frequencies. So for this one, it says an oblique angle, which is a non-right angle. So as you can see, it's the little lines that go, the rainbow lines that go through it, and that's what it's talking about with the spectral lines, which is all those rainbow colors that you see on it. And then it's bright. Change this out with an incandescent. And it's going to be smoother with less of the colorful lines, which there are some, but just less than there were on the other one. It said oblique angle. Okay. And the next one says you can quantize your whistle by whistling down a long tube, such as a tube roll of wrapping paper first, which we don't have that tube, but it says to use a flexible plastic tube. First, without the tube, whistle with a high pitch to a low pitch. Do it loudly and in a single breath. Next, try the same thing while holding the tube to your lips. Note that some frequencies simply cannot be whistled no matter how hard you try. These frequencies are called forbidden because the wavelengths are not a multiple of the length of the tube. When your whistle is confined to the tube, the consequence of quantization is of its frequencies. When an electron wave is confined to an atom, the consequence is a quantization of the electron's energy. So a high pitch to a low pitch is, and then through this it would sound, I don't know if it sounds any different going this way, but towards my ear, it's like a lower pitch than what you normally would put into it, and you kind of hear the air coming out of the tube as like a wind blowing kind of sound. Stretch a rubber band between your two thumbs and pluck it with your index finger. Better yet, stretch the rubber band in front of a windy fan. There's no fan that I have that's powerful enough to actually make it vibrate the way that it's supposed to get it vibrating. Note that the area of the greatest oscillation is always at the midpoint, which is the self-reinforcing wave that occurs as overlapping waves bounce back and forth from thumb to thumb. So it just vibrates as you stretch it apart and blow on it. This is going to vibrate to the midpoint, which is just midway between my two thumbs. And it's the same thing when you flick it with your finger. It makes that noise. Just got to get it right. And that's what happens with that. And then it says to take 2 different types of salts, 1 table salt and 1 without sodium. It says view the crystals of table salt with a magnifying glass or microscope. We don't have a microscope available. So if so, crush these crystals with a spoon and examine the resulting powder. Purchase sodium-free salt, which is a potassium chloride, and examine these ionic crystals. Both enact and crushed sodium chloride and potassium chloride, both cubic crystals built, are a significant difference. What are they? And it's a question mark. So let's see the differences. This is regular table salt. And it's already kind of crushed up, but I'm just going to crush it up with the bottom of this. Because I don't have a spoon right here. And then just looking at it with a magnifying glass as best as I can, because this is not the best magnifying glass. It just look like tiny little squares of salt to me. I can't really get any more than that from the magnifying glass. Let's see if the sodium free has any different look to it. So from first glance, it looks like the sodium free is more of a bleached color, and it looks to be more powderized. I'm not hearing as much crunching as if I were to do this one. So I feel like it might be grinded more, or more refined. Yeah, and these don't look so much like squares like this one does. This one's more circular shaped and smaller. Use toothpicks and jelly beans of different colors to build models. And so I've built a few models here. The one up here is going to be difluoromethane, which is a CH2F2, and this would be the C, the center is the nucleus, and then this would be the F and the H, and there's two of them on each of those. And then this is a ethane, which is C2 and H6, so these would be the C2s and then 6 H's. This is hydrogen peroxide, and this is 2 H's and 2 O's. You take off one of the O's and it's just water. And then acetylene, H2 or C2H2. These are the 2 C's and these are the H's. And this says, keep in mind that each carbon atom must have 4 covalent bonds, and each oxygen atom must have 2, and each fluorine and hydrogen atom must have only 1. And this is a hint, one of these molecules has a triple bond, and that triple bond is the first one, which was difluoromethane, which was the CH2F2. And then with the last experiment, we have to get a balloon. And it says, to see the action of the ion-dipole attraction, create a static charge on a rubber balloon by rubbing it across your hair. Hold this charged balloon up close, but not touching a thin stream of running water. What the charged balloon divert the path of the falling water. Your balloon is negatively charged because it picks up electrons from your hair. Why would a balloon that is positively charged also attract a stream of water? So let's go over to the kitchen and see what it does to this stream of water. Trying to get a thin stream going. It attracts to it. See if we can't get a better view of it. I think I made the balloon a little bit too big. Yeah, it comes towards it. So if it's negatively charged, and it said that positively charged balloon, so this is negatively charged because I rubbed it against my hair. It was asking if positively charged would also attract to it. I would think that the positively charged would push it away since it's opposite, but also it could be attracted because the water would be neutral. So the positive ions would be attracted to the balloon if it was positively charged. And that's it. Thank you.